Okay, welcome to another lecture. And when we left off yesterday at the end of the fourth segment, we had a little bit left to cover in section 8.6. And here it is. It's about atomic radii of the transition elements. Because so many things are different for main group elements versus transition elements, we wanted to make sure to talk about atomic radii because those are different too. The trend in atomic radii for the transition groups are different from the trends for the, the main groups. So for the A groups, atomic radii decrease going left to right. And if you remember, that's because with each space you move in the main groups from left to right, you're adding one additional electron to the outer shell of electrons, and you're adding one additional proton to the nucleus. And that results in a stronger attraction because the nucleus is getting more positive and the outer shell of electrons is getting more negative. According to Coulomb's law, that means there should be a stronger attraction between the two. And the effect is to pull the outer shell of electrons in a little bit closer to the nucleus for each time you add a proton to the nucleus and an electron to the outer shell. This can happen easily because, remember, a vast majority of the volume within an atom is empty space. The shells of electrons are far apart from each other and they're far apart from the nucleus. And so when you add a proton and an electron and you pull the outer shell of electrons a little closer to the nucleus, that basically pushes the inner shells of electrons a little closer to the nucleus, but you're really just compacting the empty space between the shells of electrons. And that's really easy to do. Compacting or compressing nothing is really easy. And so that happens to a significant extent. And so atoms get smaller as you go left to right for the main groups. Because the electron configurations for the transition groups are a little bit different, things work a little bit differently for them. Actually, it turns out that the radii for transition elements as you go left to right across the periodic table within the B groups are more or less the same. They'll change a little bit, but they only change a little bit and there's no discernible trend in the way they change. And that's because of the electron configurations. The number of electrons that are actually in the outermost shell remain the same for the transition elements because the outermost shell would be the shell with the highest number. And for transition elements, the shell with the highest number always contains two s electrons. That is, two electrons in the s-type orbital of the highest numbered shell, which, the number of the shell being the number of the period that the element is in. When you go left to right across the B groups or the transition elements, what you're actually doing is adding electrons to the d orbitals of the shell that's actually one less than the valence shell. So the n-1 shell. That's what's changing. And so that does not have as much of an effect on where the valence electrons actually are. And it's the valence electrons that actually determine the outer boundaries of the atom. So there really isn't much change in the radius of the atoms as you go left to right across the transition elements. But the trend going down a group remains the same. It's still the case that when you go down a group, whether it's in the A groups or the B groups, you're adding an extra shell of electrons for each step down a group. And that does have the effect of increasing the atomic radius. So that part of the trend is the same as for the A groups, but going left to right is actually a different trend. Okay, that brings us to section 8.7, which is about ions. Electron configurations of ions. Whoops. Be nice if you could see it. Electron configurations of ions, we've already done some of that, so some of this will be a review. Magnetic properties. which actually just has to do with whether there are any unpaired electrons in the electron configuration, which you can tell if you draw out the orbitals graphically, like we've already seen. And radii. And I'm just going to write IE for ionization energy. And we'll find out what that is when we come to it. So what we're looking at here is basically periodic trends. Periodic trends for ions. Okay, so first of all, electron configurations. And magnetic properties. Those are related to each other because, like I said, basically it'll have magnetic properties if there are unpaired electrons in the electron configuration. So first you'd have to find the electron configuration, then you could decide whether it has magnetic properties. Okay, to form the electron configuration of an ion, first of all, how you go about that depends on whether it's a positive ion or a negative ion. So for positive ions, and here we're basically talking about ions of metals, and basically you're going to need to remove one electron for each unit of positive charge. So if it's a +1 ion, you remove one electron. If it's a +2 ion, you remove 2 electrons, and so on. And they come from the highest energy orbital of the highest number shell. And for highest number of shell, we're talking about the highest energy orbital with the highest number for n. And this means that the first electron removed is not necessarily the last one you put in. So the way we normally form the electron configuration for an ion, positive ion, is that you write out the electron configuration for the neutral atom and then decide which electrons you need to remove. And like I said, the first ones that you remove will come from the highest energy orbital of the highest numbered shell. If you're dealing with a transition element, though, remember that the last electrons you added would have been gone into the d orbitals in the second to highest shell. So if you're in period 4 doing one of the transition elements in period 4, the last electrons in would have gone into the 3d orbitals. But when you're forming the ion, the first electron to leave is going to be from the 4s orbital, even though those were not the last ones you put in. So that's important to remember. It's always the highest energy electron that leaves first, even if it's not the last one you put in. For the main group metals, it actually will usually end up being the last electron you added, will be the first one out. But it's for the transition elements that it's not going to be the last one you added. That will be the first one to leave. So for the main group metals, in other words, the A group metals, the electron configuration of the ion will be the same as the configuration for the last previous noble gas. And I mean the last previous noble gas in terms of atomic number. And because that's really why the main group metals form the ions they do. It's because forming that ion by losing the number of, basically by losing its entire valence shell, like sodium loses 1 electron, well, that's its entire valence shell. And calcium loses 2 electrons, well, that's its entire valence shell. And you end up with the same electron configuration as the last previous noble gas, which is really stable. And that's why these ions form, is because it leads you to an electron configuration that's much more stable than what you started out with. Okay, last previous noble gas. For a negative ion, and so this up here is plus, this here is minus. For these, we're talking main group nonmetals. Although that's a bit redundant because all of the nonmetals are in main groups. Basically, what you do is you add the requisite number of electrons. You basically just write the electron configuration for the neutral atom and keep on adding electrons until you've added the number of the charge. So basically, if it's a -2 ion, you add 2 more electrons to the neutral element's electron configuration. Keep adding more electrons to the electron configuration. Okay. And what you usually end up with is the electron configuration of the next noble gas. And again, that's why the nonmetals form negative ions, is because they only have to gain a few electrons to get to that stable electron configuration, which is the same as the next noble gas. Fluorine has basically just 1 less electron than neon does. And so it'll really, really want to gain that 1 electron. But once it does, it's happy because it's stable. And so you end up with the F- ion having the same electron configuration as neon. And some examples here, sodium, the element, I'm putting a little 0 as a superscript after the symbol just to sort of remind us this is the neutral element with no charge on it, has 11 electrons. And so you have a configuration of 1s2, 2s2, 2p6, 3s1. And that would be basically what I've just underlined is the electron configuration of neon. Plus, sodium has that 1 electron in the 3s level. So you could also represent the electron configuration of sodium atoms as being this. Well, sodium ions have a +1 charge, which means they lose the electron in highest energy orbital of the highest number shell. The highest number shell is 3, and the only electron there is in the s orbital, so that's the electron we lose. The 3s1 goes away, and we end up with 1s2, 2s2, 2p6. That's 10 electrons, which is the same electron configuration as neon. It's important to remember in cases like this that sodium is not becoming neon. That's why we make sure to put the symbol for neon in square brackets instead of just writing an E, because we want to keep in mind that what we're talking about here is that the sodium ion has the same electron configuration as neon, but that doesn't mean that it actually is neon, because it still has the nucleus of sodium. It still has 11 protons. Neon only has 10 protons. Sodium plus ions have 10 electrons, just like neon does, but they still have the number of protons and neutrons that sodium has. So basically what's going on here is that sodium plus ions are kind of masquerading as neon, you could think of it as being. They kind of look like neon from the outside, which allows them to be stable, but they're really still sodium down underneath. Negative ion, say oxygen atoms, have 8 electrons, 1s2, 2s2, 2p4. And you may notice from up here, that means that oxygen is just 2 electrons short of the configuration for neon. Okay, and that's why oxygen forms a -2 ion. It gains 2 electrons, at which point it has the same electron configuration as neon. So what we would do if we come across and we wanted to do an electron configuration for the oxide ion, that is oxygen with a -2 charge, we just basically say, okay, how many electrons does oxygen have? And add 2 more electrons to that. Oxygen has 8 electrons of its own. When it forms a -2 ion, that means it has 2 more, which is 10. So basically, you just write out an electron configuration for something that has 10 electrons, which is, by the way, neon. So there you go, 1s2, 2s2, 2p6. And therefore, we can call it also neon in square brackets. Again, it doesn't mean that oxygen becomes neon. It means that it kind of masquerades as neon. It looks like neon from the outside because it has the same number of electrons. But it still has the nucleus of oxygen. All right, as for magnetic properties, there's basically 2 ways that an element, well, basically 2 aspects to magnetic properties for an atom. Either it's affected by magnetic fields or it isn't. That's the extent to which we really care about it right now anyway. And if the atom or ion has unpaired electrons in its configuration, then it will be affected by magnetic fields. And being affected by magnetic fields is known as being paramagnetic. And you might guess that on the other hand, if there are no unpaired electrons in the configuration, then it's not affected by magnetic fields. But what's that called? We'll get to that in a moment. Okay. That's diamagnetic. So unpaired electrons means it's paramagnetic, which means it is affected by magnetic fields. If there are no unpaired electrons, then it is diamagnetic, which means not affected by magnetic fields. And you can tell whether there are any unpaired electrons in the electron configuration first by writing out the electron configuration in the compact form that we usually write it out, but then you have to look at the, basically it's going to be each type of orbital. For the s orbitals, if there are 2 electrons in an s orbital, then there is nothing unpaired. For the p orbitals, you have to remember that the degenerate orbitals fill singly. So if there's anything less than 6, then there's going to, in the p orbitals of any given shell, then there's going to be at least 1 unpaired electron. Because remember, if P1, 1 p electron will go in like this, 2 p electrons will go in like this, so that's 2 unpaired electrons. The third one would go in like so. The fourth one would go like this. You've still got 2 unpaired electrons. The fifth one would go like this, so you've still got an unpaired electron. And it's only when you reach P6, like we have here, that they're all paired up again. And then, of course, there's also the d electrons where you could have unpaired electrons. Or F, if I'm really in a sadistic mood. As for ionic radii, as opposed to atomic radii, it takes a little bit of thinking to come up with basically the reasoning behind why the ionic radii are the way they are compared to the atomic radii. For the atomic radii, it's pretty simple and straightforward. But for the ionic radii, like I said, it's a little more complicated. Formation of a cation or a positive ion means loss of electrons without losing protons. So for the main group metals, which are the main group elements that form positive ions, so for the main group elements that form positive ions, ion formation means loss of the entire valence shell. Because we saw that with sodium. The valence shell is the 3s1 electron, and sodium forms a +1 ion, so it loses 1 electron, and the 1 electron it loses is that 1 electron in the s orbital of shell number 3, and that is the entire valence shell. And it works similarly for all of the other main group metals. They lose the entire valence shell when they form ions. And because of this, a positive ion will be smaller than the atom it's derived from. even in the transition metals, when you form a positive ion, you're going to be losing at least some of the electrons in the valence shell. That's kind of the difference between the main group metals and the transition metals. With the main group metals, when you ionize it, you lose the entire valence shell. With the transition metals, when you ionize a transition metal, you lose maybe the entire valence shell, or you may only lose one of the electrons in the valence shell. Depends on which element you're talking about. Even so, you've lost part of the valence shell, and that means less attraction between the valence shell and the nucleus. And so the positive ion is still, sorry, in that case, the positive ion, actually, never mind. If you lose the entire valence shell, the positive ion is certainly going to be smaller. If you lose part of it, that's a more complicated case, so they might actually end up getting bigger. I'm not sure about that. I'll have to look into that. So keep in mind that what we say here for the cation being smaller, that's for the main group metals. But it's sometimes that's definitely true for the transition metals, but it could sometimes not be true. So we'll stick to the main group metals for now. So for an anion, okay, formation of an anion is done by addition of valence electron or electrons to fill the shell. And of course, as we've seen, you normally end up with the same electron configuration as the next noble gas in terms of atomic number. Again, the number of protons doesn't change. And the extra, now you might think that with extra electrons in the valence shell, that they would be, okay, so the charge in the nucleus didn't go up, but the charge in the valence shell did. So you think, well, they'll be more strongly attracted to whatever charge still remains in the nucleus. And so the atom should get smaller. But actually, it ends up getting bigger. And the reason is that more electrons in the valence shell means that they repel each other, the other electrons in the valence shell, that much more. And that causes them to spread apart a little bit more. And that is enough to overcome any additional attraction from the protons in the nucleus, or to the protons in the nucleus. Okay, the extra. So the extra electrons in the valence shell repel each other without any extra attraction, or without much extra attraction anyway. So the net effect is that the anion is larger than the atom it's derived from. And also, as we've seen, actually, for any given main group element, the goal in forming an ion is essentially to reach the same electron configuration as the nearest noble gas. Because of that, you end up with a whole bunch of ions that can have the same electron configuration, even though they will have, different nuclei and different charges on them. They'll end up with the same electron configuration. So for instance, for argon, argon has 18 electrons and 18 protons. And looking at some of the some of the ions that have the same electron configuration as argon, we find potassium +1, because potassium is the first element past argon in the periodic table. And so when potassium loses its one valence electron, it ends up with the same electron configuration as argon. Potassium plus has 18 electrons, but it has 19 protons, and it has an ionic radius of 133 picometers. Another isoelectronic ion is calcium +2. That also has 18 electrons, but it has 20 protons. And that has an ionic radius of 99 picometers. As you go across the periodic table, there's also sulfur, which will gain 2 electrons to reach the same electron configuration as argon, in which case it has 18 electrons, but only 16 protons. And that has 184 picometers as its radius. So you can see as the number of basically the number of electrons is staying the same. As the number of protons goes up, the radius goes down. And 16 actually, because that's the lowest number of protons, it has the biggest radius so far. There's also one more, Cl-. That has 18 electrons and 17 protons and a radius of 121, or 181, sorry. And so you can see how the radius changes as the number of protons changes, even though the number of electrons is not changing. So what we're saying is that increasing number of protons combined with the same number of electrons results in the valence electrons being drawn in closer. And that means a smaller radius for the ions. And then we have ionization energy. Ionization energy is basically just how much energy do you have to put in to get a valence electron away from an atom. When they measure these values, the atoms are in the gas phase. And of course, most of the elements we're dealing with are not in the gas phase, but the trends should still be valid. The relative numbers should still be valid. And when we talk about removing an atom, we mean removing an atom. Well, they usually say to an infinite distance. I mean, obviously, in practice, there's no such thing as removing an atom to an infinite distance. It would take an infinite amount of time and an infinite amount of energy to remove an electron to an infinite distance. But in practice, what we mean by infinite distance is far enough away that the electron experiences no interaction, no attraction, and no repulsion from the parent atom, the atom that it came from. This value is positive for all elements. So that means that you always have to put energy in to get an electron away from an atom. No matter what element it is, even if you go for something like cesium, which gives up electrons relatively easily compared to other elements, you still have to put some energy in. For some elements like cesium, that energy that you have to put in might be outweighed by the energy that the atom releases once it's ionized. So for instance, for something like cesium, ionizing the cesium stabilizes the element enormously. And so you put some energy in. It only takes a little bit of energy. You put a little bit of energy in order to get that electron away from it. But once you take that electron away from it, the atom is much lower in energy than it was before. It's much more stable because it has a noble gas electron configuration. And the amount of energy it releases is actually, when it's stabilized, is actually much greater than the amount of energy you have to put in order to get the electron away from it. And so overall, the process is actually spontaneous because the amount of energy that's available to be released due to stabilization is so much greater than what you would actually have to put in to get the electron away from it. So the overall process is, can be, for metals anyway, especially for the group 1 metals, it can be basically spontaneous. Essentially, that's what's happening when we say that the group 1 or alkali metals are extremely reactive. Well, the way in which they react is by ionizing. When you throw sodium in water, you see it zipping around on the surface and then it blows up. But basically what it's doing is the sodium metal itself is ionizing and becoming part of sodium hydroxide. The sodium in sodium hydroxide, though, is a sodium ion, Na+. So the sodium has ionized as part of that process. And the reason that zips around the surface is because it also basically causes the water to decompose and give off hydrogen gas. And it's the hydrogen gas that sort of propels the piece of sodium around the surface. The reaction is also extremely exothermic, meaning it gives off a lot of heat, and the heat is often enough to ignite the hydrogen, which is why it often blows up. But anyway, all of that is sort of surrounding the fact that the sodium is ionizing. Okay, so, right. So the positive value, that is the amount of energy you have to put in to take an electron away, is smaller for metals than nonmetals. Especially the alkali metals. And there are also multiple ionization energies. And there is a first ionization energy for any given element, which corresponds to the removal of the first electron. And that first electron will come from the highest energy orbital in the highest shell number. And there's also a second ionization energy, which corresponds to the removal of a second electron after the first one that's removed. And of course, the second electron would also come from the highest energy remaining orbital of the highest shell number. And there's a third ionization energy, and that's for the removal of a third electron, and so on and so on. Basically, you can lay out ionization energies for each electron an element has until you run out of electrons. Basically, the ionization increases as more electrons are removed. So second ionization energy is bigger than the first ionization energy, and that goes for any element, metal or non-metal. The third ionization energy will be bigger than the second ionization energy and will be much bigger than the first ionization energy. And again, that goes for any element. For something like sodium, and exactly how they relate to each other really depends on which or what charge ion the element likes to form. So for something like sodium, which generally likes to form +1 ions, the first ionization energy, yeah, it's positive, but it's not huge. The second ionization energy, though, if you try to take away one more electron from sodium, that is huge. The second ionization energy for sodium is about 10 times bigger than what the first ionization energy is. And that's because once sodium has lost that first electron, it's stable and it doesn't want to lose any more. So you try to take a second one away, it's going to put up a fight. Anyway, we've got to go on to trends in ionization energy, but I notice we're well over time for this part of the lecture. So I better stop here and then go on to part B in a moment.